During the HAZOP study, there was a recommendation to install a PRV because of the high pressure, low pressure interface. This is an operating high pressure system where we have multi-phase flow and separated liquid goes to the second stage of stabilization for the condensate before sending to the storage through this control valve. As we can see, HP interface has an operating pressure of 10 bar, while low pressure interface has an operating pressure of 1.5 bar. Qualitatively speaking, and in compliance with API 521, this gas blow by through the control valve failure, it will necessitate an overpressure protection. So this is qualitatively speaking. There is no dynamic assessment upfront to be done to establish the need to have PRD. So this is just an over-conservative approach in API. Whenever you have an HPLP interface, PRV is needed. And to comply with API calculation, I did this quick assessment in Aspen HYSYS, and I have defined the operating condition and the design condition, and this is the selected scenario, control valve failure. And considering the upstream pressure, which is basically the design pressure of the system, or the maximum operating pressure upstream, downstream, will be the set point of the recommended PRV to protect the low pressure interface from high pressure system. And based on that, the steady state calculation and all these calculation is complying with API 521. And calculation has recommended J orifice with a predicted relief load 1,829 kg per hour. So this is the key outcomes from the steady state calculation, but these calculations is assuming that we have an overpressure scenario. Once and following the control valve failure, the low pressure interface will see high pressure, which might exceed design pressure of that vessel. And based on that, we need to have PRV. The same analysis will be done using dynamic simulation. Dynamic simulation, as per API 521 section 433, can be used in pressure relief system design and assessment to calculate transient pressure increases in the system. And the key objective from calculating the pressure increase dynamically is to calculate the required relief rate from individual PRDs. The reason for that conventional method for calculating relief load are generally over-conservative and can lead to overly sized relief system. And from that perspective, we have improved and enhanced the steady state a little bit, including the basic process control system, to see the knock-on effect and the consequences, whether it is positive or negative, on system dynamic response during relief load. In dynamic, we have created an event scheduler considering all potential scenarios. Namely, that scenario has been considered in HAZOP, considering the fail open for the level control valve, which will be followed by the entire liquid from the HP interface to LP interface will go through, and this theoretically and qualitatively should result in an overpressure. We will see in dynamics whether this is a credible scenario or not. So again, to conclude, qualitatively, when we consider a blocked outlet case, fire case, control valve failure, tube rupture case, this assume an overpressure scenario. Dynamically, quantitatively, it may not result in an overpressure. So though I have control valve failure, not necessarily to see an overpressure in the system. And the definition of overpressure as per API 14C, if the transient pressure increases above design pressure of the vessel, this is a definition of overpressure. So my key objective is to see the pressure rise in the LP interface, whether it is going to exceed the proposed set point of the PRV located on the LP interface or design pressure of the LP interface. This indicates an overpressure. Now I'm ready to run this scenario in dynamic simulation, considering the LV100 fill open, and this chronology has been established in event scheduler. Now what I need to do is to run the integrator under dynamics and to see the consequences. Once I have this fill open and all liquid containment from HP interface to LP interface alongside some entrain gases to the LP interface, what would be the consequences? Basically, considering the existing basis process control system is not a substitute to replace the pressure relief devices, but it considers an element of reality, because at the same time we have this control valve is functioning and the overhead gas control system is functioning. All these things will lessen the relief load and relief demand on the LP interface, and that was a recommendation from API 521. So now the simulation is running, and in few minutes now, as I can see, this has become 100% fill open. I can see marginal increase in transient pressure at the LP interface. Liquid here is actually decreasing, and it makes sense. This valve has significantly increased, and the entire liquid from HP to LP interface will migrate. As I can see here, the transient pressure fluctuation in the LP interface, it is going up and down. That was the slight increase, but very quickly has been damped down because of the gas control system. But irrespective of the dynamic interactions has taken place, I can see, though I have control valve failure, which is credible scenario and key initiating causes for overpressure, but dynamics has proven there is no overpressure. The pressure increase in LP interface didn't exceed the set point of that proposed PRV. Someone would argue, I don't need to rely on any existing IPL in the system. So this pressure control system, level control system on the LP interface should not be taken as a credit. And I need to assume there is no any means of protection except the ultimate protection, which is the proposed PRV. We have this engineering debate in industry, and whether it is old school or over conservatism approach to the existing facilities, but also this can be done just to raise an awareness and to demonstrate the key differences between the conventional approach and the dynamic approach. So also this can be done. In event scheduler, the chronology has considered that at the time this valve will fill open, this control valve will maloperate and will consider failure. So this PV will be off. It will not function. At the same time, this level control valve is 100% opening. And this actually exacerbates the situation, and it puts a huge demand on the LP interface, which means the transient pressure will significantly increase. We will see from dynamic what would be the corresponding relief load and whether this relief load is close match to the one resulting from the steady state, a little bit more, a little bit less. This is the element of optimization, not optimization, it is the element of reality and the accurate prediction, accurate calculation of a specific parameter. This parameter is so crucial down the road to reassess the associated process piping connected to the PRV upstream and downstream all the way to the tailpipe and the flare knockout drum. So now the situation is running and this valve now is 100% opening and this valve is fully closed, is not functioning. I can see significant increase in the pressure inside LP interface. So far it didn't reach the set point. I can see it has reached the set point and the corresponding relief load from that scenario is 220 kg per hour. Going inside the PRV, see the percentage of the valve opening is 4.5. This is very slow, very low percentage. Just to refresh our mind from section 1, based on the steady state calculation, the steady state calculation of API has concluded relief load of 1800 kg per hour. 1800 kg per hour, whereas here I have 220 kg per hour. So this is significant differences between the steady state and dynamic. Though I have added unjustified chronology and set up to this scenario, I have assumed double jeopardy. This valve will fail and at the same time this valve will fail. The resultant relief load is so less compared to the steady state assessment. This is what I wanted to conclude from this Path to Power series. You need to apply your engineering judgment based on the system criticality and based on the type of facilities, whether it is greenfield or brownfield. If it is greenfield, you have all free to consider all conservatism you need to consider to ensure inherently safer design. But when it comes to the existing facilities, to apply and to reinstate the code over conservatism retrospectively on existing facilities is so demanding from time perspective, cost perspective. So you need to migrate a little bit from the steady state concept to dynamic concept to see the accurate prediction specifically for relief system.